Alrighty, good morning everybody, and welcome back to Calc 1. Plan for today is to continue our discussion of Standard 15, looking a little bit more at the first derivative test, as well as its friend, the extreme value theorem. Got my usual office hours today and tomorrow. Today at 11 and at 2, tomorrow at 10 and at 1. And as far as homework goes, I got web work up and running again. I had to contact the people who manage the server for us, and it was complicated, and I hate their system, and let's hope this doesn't happen again. But yeah, you have homework, I think it's 17, I forgot to check the number, that's due on Friday, and also don't forget, Exam Friday, Standards 1 through 14. If we finish Standard 15 today, I'll tack on a Standard 15 question. I'm not sure if that's going to happen. Pass back everything that I have. Should be all the retests up to this point. In addition, if you go look on Canvas, I've posted solutions for everything. Not the retests, but all the version 8, the in-class quizzes, and all my solutions for all the packets to date. Anybody have any questions or comments before we get started? Okay, my apologies to a few of you out there on this one. Can an English major learn trig? No. Of course he can't. Feel the need to apologize for that one. It is untrue. Anyone can learn trig, even you. Okay, so last time in class we were looking at properties of the first derivative, where last time we mainly focused on looking at graphs of functions and seeing how do the ideas of local max and mins as in comparison to absolute max and mins occur looking at a graph. And the theorem we had was the first derivative test, which says that if you have a continuous function f of x and you want to look for local maxes and local mins, then your function is going to have a local max at a value a if f prime goes from positive to negative at a. Meaning if your slopes are going upwards to the left of a and then downwards to the right of a, you have to have a local max at that point. Similarly, if your first derivative goes from being negative to positive, meaning your function goes from heading downwards to going upwards at your point, then you have to have a local minimum there. And we also said that the only possible points where those can occur are at critical points, which are points on your function where f prime is 0 or undefined. And those are only potential points where f of x could have a local max and min. But as we saw last class, just because you have a critical point doesn't necessarily mean that you have a local max or min. Where we could also have a situation like this going on with our function, where maybe at this point f prime is 0, but we don't have a max or a min. If our derivative does something like going from negative to negative again, not necessarily enough to tell us we have a local max or min. And so last time we had started looking at the function f of x equals x cubed minus 3/2 x squared minus 6x plus 5. And our goal was to find where does this function have a local max, local min, where is it increasing, and where is it decreasing. And to see if we can find all that information without actually having a graph of the function in front of us. So with a problem like this, we said that the first step to do is always going to be to find our critical points to start with, because those are going to be the potential places where our function could have a local max or a local min. So what should we do if we want to find where the critical points of this function are located? I think we found the critical points last time, but then ran out of time after that. Rachel?
You would take the derivative of the function and then set it equal to 0.
Yeah, we check to see, we take the derivative f prime of x and see where is that 0 and or where is that undefined. So we differentiated this last time and got 3x squared minus 3x minus 6. And we said that this is defined everywhere because it's a polynomial. So the only potential points where we could have a local max or local min of this function are points where our first derivative f prime is 0. And so if we set this equal to 0, last time I think you all told me to factor out a 3, and then we can factor the x squared x minus 2 to get x minus 2, x plus 1, and found that we had two critical points of our function, which were at x equals 2 and at x equals negative 1. The 2 points on our function where our derivative is either 0 or undefined. And that's where we left things off the last time. Any questions or comments so far? So the next step, once you know where your critical points are, is we need to check what f prime is doing on each side of all of our critical points. And what that means, in terms of what I like to do, is I like to draw out a little number line and put the critical points that we have on our number line. And then what we can actually do with this little number line here is we know at negative 1 and at 2, f prime is going to be equal to 0. That's what we just found in step 1 here. And then to determine what f prime is doing on each side of our critical points, what I mean by that is I want to check if f prime is either always going to be positive or always going to be negative anywhere between our critical points, say at negative 1, between negative 1 and 2. And so one way you can actually check this out is to find a number, pick a number x between negative 1 and 2, and plug it into f prime to see if we come up with something positive or something negative there. Hannah, give me your favorite number between negative 1 and 2. 0 seems like a good point to check. So if we check out f prime of 0, we'll get, what's f prime of 0?
Negative 6.
And we'll get 0 minus 6. Thank you for choosing 0 and not trying to be mean to me and say, all right, Dr. Arstle, check out f prime of 7 pi over 16 or something. But what we particularly care about is that it's going to be negative. And what that tells us is that in between our critical points at x equals negative 1 and 2, f prime is always going to be negative between those two values of x. At x equals negative 1, it's 0. At x equals 2, it's 0. If we pick a point in between and see that f prime is negative there, that means that f prime has to be negative everywhere between those two values of x. With the reason being, if somewhere between negative 1 and 2, it were to change from being negative to positive again, that would have to occur at a critical point. And as we've seen, there aren't any critical points between x equals negative 1 and x equals 2. The other thing that we have to do is we have to pick points kind of to the left of our leftmost critical point and to the right of our rightmost critical point, meaning we need to pick a value of x to the left of negative 1 and to the right of 2 so that we can see what's f prime doing on the other side of our two critical points. Riley, can you give me a value of x to the left of -1? -2? Seems like a pretty reasonable choice. I don't actually care about what f prime of -2 is. So I don't really feel like plugging -2 into this function because that looks ick. It's not actually that bad, but a little bit ick. You can actually use a shortcut method and say f prime and see what would happen if we plugged f prime of 2 in down here into this 3 times x minus 2 times x plus 1. And if we do that, we're going to find out that we're going to get a positive number here, a negative number here. -2 minus 2 plus 1. We're going to get a negative number here. Oh, yeah, oh, that's right. And if we're multiplying something positive by something negative by something negative, what type of answer are we going to get, Zach? Yeah, we're going to get some positive number. Doesn't matter exactly what it is. 3 times -4 times -1, which is what, 12? But what we really care about is that our derivative at -2 is going to turn out to be something positive. Which is going to tell us that everywhere to the left of x equals -1, our first derivative is always going to be some positive number. Because if it were to change from being positive to negative somewhere to the left of -1, that means that there would have to be some other critical point to the left of -1, and we know -1 is our leftmost critical point from the work we did here. Finally, the last thing that we need is we need to check f prime at some point to the right of x equals 2. Elise, can you give me a value of x to the right of 2 that we can check? 3 seems like a pretty reasonable choice. So if we take f prime of 3, again, I'm going to use this factored form down here just because I think that's a little bit easier to work with if all we're trying to do is to find, are we getting something positive or negative? Let's see. 3 is going to be positive. Or let's just write this out. We'll get 3 times 3 minus 2 times 3 plus 1, which is going to be a positive number times a positive number times a positive number. And if we multiply 3 positive numbers together, is our answer going to come out to something positive or something negative? That?
Positive.
Are you positive?
I hope so.
Indeed. You come out to some positive. I'll be yes. So now, what's the point of all this? The point of all this is so we have some idea of what's going on each side of all of our critical points with f prime. F prime goes from being positive to the left of -1 to being 0 at -1 to being negative in between -1 and 2 to being 0 at 2 to being positive to the right of 2. And now we're finally ready to use the top half of the first derivative test to tell us at our 2 critical points what's going on. Do we have a local max, a local min, or potentially neither? So let's start with, Mackenzie, pick -1 or 2. Okay, at x equals -1. What's going on with our derivative? F prime is positive to the left of -1 and negative to the right of -1. So we can say at x equals -1, f prime of x goes from being positive to negative. So f of x has a blank at x equals -1. So our function to the left of -1 is going to be increasing. To the right of -1, it's going to be decreasing. We look at kind of what does the general shape of our function look like. So what does the first derivative test then tell us has to happen at x equals -1? What type of extremum, Mackenzie, do we have?
It has to have a local max.
Yeah, it has to have a local max. Because the first derivative test says if f prime goes from positive to negative, meaning your function goes from increasing to decreasing at a point, then that has to be the site of a local max. And similarly, we want to look at x equals 2. We can see that our function goes from having a negative first derivative, so it's decreasing, to having a positive first derivative, so it's increasing to the right of 2. So f prime goes from negative to positive, or minus to plus. So f of x is going to have what going on at x equals positive 2? When?
At least a local min.
It's going to have a local min. Because local min happens when your function goes from decreasing to increasing again. Get a better piece of chocolate, so it's almost worn out. So f of x has a local min at x equals 2. So the moral of the story is, once you know where your critical points are, you can find what is f prime doing on each side of all of those critical points. And I like to do that by looking at a number line like this and kind of picking points in between your critical points and on the far left and far right side. Thank you all for picking 0, -2, and 3, and not horribly nasty numbers to check. And then once you have this number line in front of you, you can kind of use what f prime is looking like between those points to say exactly what types of critical points you have. Do you have a local max or a local min? If for the sake of argument, we had something like this, where f prime went from negative to negative at 2, and we had a graph that was sort of looking something like this, we would have said it doesn't have either a local max or a local min. Questions, comments? Yeah, John?
Why did you keep the 3 in the function as 3 of x minus 2, x plus 1? Like, wouldn't you divide by 3 to cancel out?
Well, like over here,
Yeah.
technically you could, and just say like, well, you could divide both sides by 3 and say, oh, if 3 times x minus 2 times x plus 1 is 0, then x minus 2 times x plus 1 is 0, and then x has to be 2 or -1. I kind of skipped a step there.
So then why'd you keep it over here?
Good question. Because it mattered for determining the sign of the derivative between those points. So for instance, if our derivative had come out to something like -3 times x minus 2 times x plus 1, then this -3 would have mattered because we would have gotten a minus times minus times minus, a minus times plus, and it would have changed the sign of the derivatives to the far left and to the far right. And also at 0 itself, this would have become a positive 6. So the fact that we had a positive 3 here versus a -3 could have mattered in determining whether f prime went from plus minus plus or whether it was minus plus minus.
Okay.
Good question though. So the last thing I want to look at for this problem, I think I asked this in the packet, is where is this function increasing or decreasing? And once again, I think our number line is going to be helpful in answering this question. Keeping in mind that f of x is going to be increasing, meaning it gets bigger from left to right, anywhere that our first derivative is positive, and it's going to be decreasing anywhere where our first derivative is negative. So with that in mind, Josh, where is our function going to be decreasing?
It would be decreasing from negative infinity to positive 2.
All the way from negative infinity to positive 2?
Yeah.
If f of x, so you're saying f prime is going to be negative everywhere to the left of 2?
Is it increasing or decreasing?
Sorry, I said decreasing.
Oh. It would be decreasing from negative 1 to 2 then.
Yeah, I think it's going to be decreasing from negative 1 to 2 because that's where f prime is going to be negative. Sorry, I tricked you. I asked for decreasing first. It's going to be decreasing over the interval from negative 1 to positive 2. And if you want, you could write that out you could write that out this way if you're more comfortable with that notation. For x between negative 1 and 2. How about increasing? Okay, Josh, you want to redeem yourself?
Be increasing from 2 to infinity, and negative 1 to infinity, negative 1 to negative infinity, or switch it around.
Yeah. I'm going to say from negative infinity to negative 1 and from 2 to infinity. I like to always list mine out from going from left to right. But the fact that f prime is positive everywhere to the left of negative 1 and positive everywhere to the right of 2 is going to tell us that over the intervals where x is less than negative 1 or when x is greater than 2, f of x is going to be increasing over those intervals. So if we wanted to, we could even draw a little graph of what f of x is probably going to look like now. Let's see, if f of x changes from at negative 1 and 2, it's probably going to look something a little bit like this. Where it's increasing to the left of negative 1, decreasing from negative 1 to 2, and then increasing again to the right of x equals 2. Any questions, comments, or concerns? This is the basic procedure you would always do if you're trying to do a first derivative test. Look for your local maxes and mins. If you don't have a graph sitting in front of you, is find your critical points. You make a little number line like this. You check what f prime is doing between your critical points and on the far left and right hand side. And then use the first derivative test to say, if f prime is going from positive to negative, we have a local max. Negative to positive means we have a local min. Wherever f prime is positive, we have increasing behavior. Wherever f prime is negative, we have decreasing behavior. Let's try out one more example where we put this into practice with another function that's a little bit spicier than this one. So next function I want to look at is h of x equals x squared minus 8 divided by x plus 3. And once again, I'm not going to give you a graph to look at. I'm just going to give you a formula for the function instead. Okay. Sorry, I put you on the spot, Daniel. I love glaring at students when I can hear them or when I see them whispering. I don't actually really care. So I want to find where this function h of x has local max, local min, where it's increasing, where it's decreasing. What should we do? Start things off. So I think you answered this question for the last function, so I'm going to give someone else a go. What should be our first step, and which is going to be the same as the first step for the previous function in looking for local max and local min points, Riley?
Finding the critical points.
Yeah, let's find our critical points to start things off. So Riley, what should we do in order to be able to find our critical points?
I like to set it equal to 0.
Yeah, you take our derivative and see where is our derivative 0 or undefined would be a good step. All right, we have x squared minus 8 all over x plus 3. Alan, what rule do you think we're going to need to use in order to differentiate?
The quotient.
Sounds like a quotient, looks like a quotient rule to me. So we can do our whole low, d high, derivative of x squared minus 8 is 2x minus high, d low, derivative of x plus 3 is just 1. Merrily. Low squared down below. So I get x plus 3 times 2x minus the quantity x squared minus 8 times 1 all over x plus 3 quantity squared. Is there anywhere where this expression, let's start off with undefined. Is there anywhere that this expression is going to be undefined? Kenzie? Why is this undefined at -3?
Because when you set x equal to, or not, when you set the function equal to 0, then x is equal to 3.
I don't think if we plug in -3, this whole thing is going to come out to 0 necessarily.
-3 plus 3 is 0, and you can't divide the function by 0.
Oh, so you're saying that if we plugged in -3, we get a 0 in the denominator, which would make the whole thing undefined? Avery, is that what you're going to say? Yeah. I would say h prime of -3 does not exist. Since don't divide by, since you would have to divide by 0. I'm just going to say h prime does not exist. See? PSA, don't divide by 0. I think that's going to be the only point where our derivative h prime is undefined. I think for any other value of x, this is we could plug in and this will come out to some number. What can we plug in for x that's going to make this come out to 0? I don't know if we can really find that very easily just from looking at it right now. Although maybe I spoke too soon because Avery's immediately going to jump into the fray.
Can't you set the numerator of the function equivalent to 0? Because the top is equivalent to 0, and the whole thing's equivalent to 0.
So where the denominator is 0 is going to make the whole fraction undefined, but where the numerator is 0 will make the whole fraction come out to 0. I like it. Yeah, I think that's going to be our strategy. I'm not just going to take the numerator for now. I'm going to leave the whole thing, h prime of x expression out there, for the purposes of making our second half of the problem a little bit easier. But yeah, I agree. I think that's a good way to do it. So let's rewrite our numerator here See if we can find where does that come out to 0. So if we multiply this out, we're going to get 2x squared plus 6x minus x squared plus 8 all over x plus 3 quantity squared. Or here I just distributed out the 2x times x, 2x times 3, and then distributed this minus sign to get minus x squared minus a negative 8, which became a positive 8. And if we combine these, we'll get 2x squared minus x squared is x squared plus 6x plus 8 over x plus 3 quantity squared. If we wanted to find out where the numerator is equal to 0, where x squared plus 6x plus 8 is 0, what can we do to find that out? When?
We have to factor the numerator.
Okay. How can we factor our numerator?
Well, you do technically the two numbers multiply A and C, and then add to get B. So it would be x plus 2 and x plus 4.
Let's see. 2x plus 4x would give us 6x, so they add to give us our 6 here. And 2 times 4 is 8. I like it. And is that just a stretch?
Yes.
Cool. Yeah. What values of x now are going to make our numerator equal to 0? Our numerator is of the form x plus 2 times x plus 4.
-2 and -4.
Yeah, I think we're going to get -2 and -4. So we could say that h prime of x equals 0 at x equals -2 and -4. And those are going to be the points that we have to check. -2, -4, and -3 are going to be our points in our number line where interesting stuff is happening with the derivative. That at -2 and -4, the derivative comes out to 0. And at -3, our derivative turns out to be undefined. So now, I think we can move on to step 2 for this function. So let's see, -4 is the furthest to the right, -3, -2. We know at -4, we get a derivative of 0. At -2, we get a derivative of 0. At -3, we get a derivative that's undefined. Well, now we need to check between these 2 points, or on either side of -3, what's h prime doing? To the left of -4, what's h prime doing? To the right of -2, what's h prime doing? Oh man, -2, -3, -4. There aren't any integers between there to check. So I think we have to get a little bit ugly with numbers to plug in. Let's start off to the left of -4. Logan, can you give me a number to the left of -4 where we can check out what's the sign of h prime?
-5.
Okay, we check h prime of -5. It's here. I'm just going to use this factored form, this x plus 2 times x plus 4 over x plus 3 squared. We're going to get -5 plus 2 times -5 plus 4 all over -5 plus 3 quantity squared, which is going to come out to, let's see, something negative times something negative divided by some negative number squared. And is all that going to come out to something negative or something positive in the end? We multiply 2 negative things in the numerator and have a negative number squared in our denominator. Give the sign of the cross for me there. Yeah, it's going to come out to positive. The two negatives in the numerator will come out to something positive. Our denominator will be positive because a negative number squared is positive. Positive over positive is positive. Again, we don't actually care what the exact numerical value of h prime is at -5. We just want to know, is it going to be positive there or negative there? Yeah,
Do we need to worry about the denominator really, or can we just plug stuff into our derived numerator?
good question. I think in this case it doesn't, for this specific function it doesn't matter, but in general it would. Because if we had something like an x plus 3 cubed in our denominator, then we would have negative times negative over negative cubed, and that would turn out to be negative instead. So similar, this is similar, John, to what you were asking for the previous problem. Do we have to use the whole thing? The answer generally turns out to be yes, because based on what the denominator is doing, that could tell you what the sign of h prime is. It could affect whether h prime is positive or negative at that point. All right, let's check between -4 and -3 now. Cecilia, what's a good value of x to check between -4 and -3?
Negative 3.5.
I guess by good I mean least bad. Yeah, so we could check something like -3.5. Let's see. I'm not even going to bother plugging in the number. I'm just going to look here. -3.5 plus 2 is something negative. -3.5 plus 4 is going to be something positive. -3.5 plus 3 is negative, so we'll get a negative squared in our denominator. And so is h prime of -3.5 going to come out to something negative or something positive here? Hayden?
Negative.
Yeah, we're going to get negative in our numerator, positive in our denominator. So this is going to come out to something negative overall. And here we've got to the point where I really don't want to have to plug in -3.5 and get an actual number for that. If I wanted to plug in -3.5 into this, that would be sad. That's why having your, like I said, having h prime of x in fully factored form can sometimes be helpful in the sense that if we just write it as the product of a bunch of different terms and or quotient, we can just look at, oh, we have a negative times a positive divided by a negative squared, and tell a lot easier, is the whole thing going to come out to something negative or to something positive? Ryan, next we need to check between x equals -3 and x equals -2. What do you, can you give me a point to check? -2.5. Y'all are picking the nicest numbers. I'm gonna erase the first part of the test. So if we check h prime of -2.5, we're going to get -2.5 plus 2 is something negative. -2.5 plus 4 is something positive. -2.5 plus 3 squared is a positive number squared. And, John, is that going to come out to something positive or negative in the end?
Negative.
I think so. We're going to get a negative number in the numerator, positive in the denominator. Whole thing's going to come out to something negative. And finally, we need to pick a point to the right of -2 to check. I'm going to pick this one. I'm going to pick h prime of 100. Just to mix things up a little bit, and also because it doesn't really matter. 100 plus 2, positive. 100 plus 4, positive. 100 plus 3 squared, positive number squared. So if we have a positive thing times a positive thing divided by a positive thing squared, Laura, what's that going to come out to? Something positive or negative in the end?
Positive.
It's going to,
Positive.
sorry. I was trying to decide if I wanted to make the same bad pun I did with Josh earlier where I said, are you positive about that? But I'll spare you. So if we look, we can see that h prime goes from being positive to the left of negative 4, negative between negative 4 and negative 3, negative between negative 3 and negative 2, positive to the right of negative 2. So now we can finally ask the question, and we'll do increasing and decreasing first this time. Looks to me we're going to be increasing over the interval from negative infinity to negative 4 and from negative 2 to positive infinity. Where's our function going to be decreasing? Harry?
From negative 4 to negative 3 and negative 3 to negative 2.
Yeah, negative 4 to negative 3, negative 3 to negative 2. Those are our intervals where h prime turned out to be something negative. Josh?
Could you just do negative 4 to negative 2 even though at negative 3 it's undefined? Or should you stop it there?
Great question. I was just about to ask you all that. Okay. I would say you could also just write that from negative 4 to negative 2 if you prefer. Since it goes from decreasing to flattening out, but only for a split second, and then goes right back to decreasing, you could say from negative 4 to negative 2 essentially in this case. Although, I don't know if it's going to be flattening out. I think we have a point where we have a local max for this function. Where does this function have a local maximum? Where if we use our number line, we want to see where does h prime going from positive to negative, meaning our function goes from increasing to decreasing. Laura?
At negative 4.
At x equals negative 4? I like it. Local max at negative 4, since h prime goes from positive to negative there. How about at x equals negative, almost gave it away. How about local mins? Ellen, are there any values of x at which we are going to have a local minimum occurring?
Yes, at negative 2.
At negative 2? Why is that?
Because the function changes from negative to positive.
Which function?
The derivative.
Yeah. We're going to have a local min at x equals negative 2, since h prime goes from negative to positive. I have a question. What's going on at negative 3? Mackenzie?
At x equals negative 3, h prime goes from negative to negative, so h of x is neither a local max nor a local min.
Yeah, since it's going from negative to negative at negative 3, we're not going to have a max or a min. In fact, at negative 3, the original function's not even defined. So technically, if something like this had happened, we still wouldn't have a local min at negative 3, because in order to have a local max or a local min, your function needs to actually be defined at that point. And in this case, at negative 3, it ain't even defined. So there are kind of two reasons to say why we don't have a local max or a local min happening at x equals negative 3. Any questions or comments about this one? Alright, nice job. So this is a general procedure for looking for a local maxima and local minima of a function. You find your critical points, you check out what h prime or f prime, whatever your function, whatever your derivative is doing between your critical points and on the far left and right sides. And then once you know that, you can use that information to determine where's your function the original function increasing versus decreasing. And also, where do you have a local max from going from h prime positive to negative? Where do you have a local min going from negative to positive? And for local extrema, it didn't happen in either of these two examples, but it's possible you could have a situation where multiple of the same type occur. Like if we had had plus minus, for instance, we would have had 2 local maxima and no local minima, and depending on your function, that's something that could potentially occur. So, next thing I want to talk about is, now that we know how to find local maxima and minima, how do we find absolute maxima and absolute minima? And for that, we're going to need another theorem, or this one is called the extreme value theorem. I'm going to skip the next couple pages in the packet and kind of leave that to you as a practice problem for you to look at. So, for finding absolute extrema, we have this extreme value theorem. Extreme because it was named by a pro skateboarder or something. No, because extreme here just means extrema, meaning like maxima or minima. From here on out, I'm probably going to abbreviate this as EBT, which says that if you have a function f of x that is continuous over a closed interval from a to b, then 2 things happen. First of all, f of x has to have an absolute max and an absolute min over this interval. And also, we can say what are the possible places where that occurs. That has to occur, the absolute max and absolute min have to occur at either critical points or the end points of your interval. So the 3 possible places where we could have an absolute max or min is at x equals a, x equals b, or a critical point of our function inside the interval. And the reason for that, if we just draw a quick picture here over to the side, is if we have some function let's say here is our x equals a, here is our x equals b, and we're only looking for absolute maxima and absolute minima between a and b. So from this point on the left over to this point on the right, if we want to find where does this function, where could it possibly reach its absolute largest value and its absolute smallest value inside that interval, meaning we only care about x that are between a and b, we could have we have to check 4 points in this case. Our 2 critical points, we'll call this point C, we'll call this point D, as well as the 2 endpoints of our interval. So if we're only looking at the closed interval from a to b, Vera, if you look at this function, right, probably shouldn't ask someone who's maybe can barely see the function. I'll ask. Okay, good. Then I'll ask. At what value of x from a to b is our function going to take on its largest possible y value?
Would that D? I mean B?
Also, probably didn't help that I didn't label them a, b, c, d from left to right. Yeah, I would say at x equals b. Over this interval, this is the largest y value is at b that the function takes on. In other words, at one of our endpoints. How about at what value of x over this interval is our function going to have an absolute minimum? Yeah, at d, which isn't one of the endpoints of our interval, but instead is going to be a critical point inside of our interval. And so what the extreme value theorem says is one of these situations is always going to happen. That if you have a function that's continuous like this over some closed interval, you're going to have an absolute max and an absolute min inside the interval, and they have to occur at either the endpoints, so A and B in this case, or any critical points that we have in the middle. And so the idea is, in order to determine where that is, you just got to check all of those points for your function. Check the endpoints of your interval, check any critical points that happen to be in the middle somewhere. Let's do an example where instead of a graph, we're given a formula to work with. Chalk. Yes, this is chalk, everybody. I know basic words. So I'm going to look at the function f of x equals 2x cubed plus 3x squared minus 72x minus 8. And I want to find where does this have an absolute max and absolute min over the closed interval from x equals 1 to x equals 4. Given this sort of problem where you're given a closed interval and asked to find absolute max and min using the extreme value theorem, I like to start at, since we know those have to occur at either the endpoints or any critical points inside the interval, I like to start off the same way that I did with the local max and min problems with the first derivative test. I'm going to start off by finding our critical points of this function. Zach, we want to find our critical points. What should we do to start?
Find f prime.
Yeah, we need to find where's f prime 0 or undefined. In this case, f prime is going to be, what's f prime going to be?
6x squared plus 6x minus 72.
And 6x squared plus 6x minus 72. Yeah, I'm on board. Zach, is that ever going to be undefined?
Nope.
It's a polynomial, so it's going to be defined everywhere. So our only critical points can occur when this comes out to 0. Good golly, Miss Molly, how can we find values of x where that's going to come out to 0? Let's get someone else in on the fun. Avery?
You can factor out a 6.
Okay, what's that going to leave us with?
6 times x squared plus x minus 12.
Okay. Cool. To make John happy, I'll divide both sides by 6. And just be left with x squared plus x minus 12 is 0. Pietro, how can we solve this equation? X squared plus x minus 12 equals 0.
Get back to x plus 4 times x minus 3.
let's see. If we do that, we'll get x squared plus 4x minus 3x comes out to a plus x. And 4 times minus 3 is minus 12. I like it. So what values of x at Petra are going to be our critical points? Yeah, we're going to get that x has to be negative 4 or x equals 3 are the two critical points. Mackenzie?
The interval is over 1 through 4, so we know x equals 3.
And so for my follow-up question, I'm going to ask which of these critical points can we automatically just throw away? Mackenzie, I think, has already answered that in the form of at x equals negative 4, that's not in the interval that we care about, so we don't care about this. This is not a potential location of an absolute max or min inside the interval from 1 to 4, because it's not in the interval from 1 to 4. 3 is, so that's one that we should consider. So the reason why I'm crossing this out is not in the interval from 1 to 4. So we have one critical point at x equals 3 that we need to check to see where we have an absolute max or min. More chalk. So now in step 2, we have our we're going to have 3 possible points, I claim, where our function over this interval could have an absolute max or min. So we're going to check our potential points for maxima / minima. So one of those 3 points is that at x equals 3, which is our one critical point inside the interval from 1 to 4. If both of our critical points had been in that interval, we would have had to include both of these in our considerations. According to the extreme value theorem, what are the other 2 values of x where we could potentially have an absolute max or min?
1 and 4,
Why 1 and 4?
because there are endpoints.
Yeah, we also need to check our endpoints. And so here, if we know that we have to have an absolute max and min, and they have to occur at one of these 3 points, we don't really need to do the thing again where we plug in f prime and check it on either side of all of these points. Instead, what I'm going to do is I'm going to make a table where we plug in our values of x, which is our critical points at x equals 3, and our endpoints at x equals 1 and x equals 4. The fact that this came out to the first 3 digits of pi is coincidental. Now you need to know what f of x is at all of those points. X equals 3, this f of x is negative 143. X equals 1, it's negative 75. At x equals 4, it's negative 120. Dr. Gerstle, how did you know that? I worked it out ahead of time. If this is a quiz question, it would be nicer numbers to work with. Or, well, the numbers are nice here, but the function f prime, or f of x, would be nicer to work with. And if you notice, these are values that we get from plugging in our potential absolute max and min points into the original function, f of x, not f prime of x this time. Yes?
Why do you do that? Like, what is the reason?
Good question. Y'all are on point today for asking me questions, a question that I was about to ask to the class. So why do we plug these into f of x and not f prime of x? I think the reason is going to be, when we look for absolute max and min, we want to find the values of x that give us the largest possible y values and the smallest possible y values from the original function, f of x, We're just looking for how big can the outputs get, how small can the outputs get. And in order to do that, we need to know what are our y values of our points from the original function. Because we're not using the first derivative test where we're checking what's the sign of f prime telling us about these points like we did to find local extrema. To find absolute extrema, you just need to know what are the y values at various points. And now, once we have this table, what we can do is find the largest y value in this table. That's where we have an absolute max. Find the smallest y value in this table. That's where we have an absolute min. Okay. Which of our x values is going to give us our biggest f of x value? Biggest meaning most, in this case, least negative.
So at least negative value, negative 75.
How about our most negative?
Negative 1.
I couldn't read my own table for a second. I was almost about to ask, are you sure about that? Then I realized, no, I'm the one who's mistaken. Yeah. So what this tells us right here is since this is the largest y value from our table, we have an absolute maximum value of negative 75 that we found at x equals 1. And similarly, we're going to have an absolute minimum value of negative 143, which we found at x equals. So the moral of the story is, when you're finding absolute extrema using the extreme value theorem, you don't need to make the number line like we did for local maxes and mins. Instead, what we do is we just find our critical points, plug them into a table with our endpoints, see which of those is going to give us our largest y value, which of those is going to give us our smallest y value, and then the smallest y value out of these will be where our function has an absolute minimum over the interval, and the largest y value is going to be where our function has an absolute max over that interval. Okay,
Put it on there.
I want to do one more example of this before I call us done with standard 15. But that is the last kind of major new concept that we're going to have. Now, do you all want a standard 15 question on the exam?
Yes. Sure.
Of course you do. It's no extra work for you. It's only extra work for you, Dr. Okay, fine, sure. I'll give you a standard 15 question on the exam, but note that on Monday we will do one more example of extreme value theorem before we move on from standard 15 to 16. Have a good rest of your day. See y'all on Friday for the exam. You're taking an exam.
That's right.
Yeah, send me an email, let me know which standard.
It might be a little bit after that.
Sure. Talk about some stuff.
Rude.
You got it.
I don't know how to pull up my own tires, and
Send me an email to remind me.
T-Rad was gonna do it. I learned how to do that.
Is it
What's
alright if I do a health test on Mondays? Does that sound good for you?
Yes, because you had the conflict.
Yes.
Yeah, sure, that's perfectly fine. Did either of these times work for you on Monday?
On Monday, yes. I love it. That would totally work.
Awesome. So I'll plan on you doing that then.
Okay.
Yeah, and I'll just set you up in the cyber for this. Have a good day.
You have your office hours.
I do indeed. 11 to 11:45 and 2 to 3.
Cool, because I thought I would bring in my former midterm, so I won't make the same mistakes again.
I want to talk about midterm taking strategies.
Yeah, because I think I don't know, there was just I think the problems being in word problem format rather than just like given equations really confused me. And looking
There's
back
going to be
over-
fewer of those this time, I would say.
Okay, yeah, I just want to make sure I fully understand what I'm doing, especially for the standards like 1 through 3. I think it's right now a lot of issues.
Sure. Yeah, sounds good. Well, talk in a little bit. Hello, Laura.
Actually, it's not just standard.
Yes. Yep, let me know which standard and come into 11 today. That should be fine. See you in a bit. Oh, you have to end.